In this video, we're going to talk about energy bar charts. Energy bar charts are just a way for us to visualize how the energy is changing when entering or exiting a system. And so there's going to be two types of energy that are represented. The first one is kinetic energy. Kinetic energy from our last unit, if we remember, is the energy of how fast particles are moving. We represent this with the arrows in our particle diagram. And the evidence that we have is the measurement of temperature. So if it is hot, then it has more kinetic energy than if it is cold, and it would have longer arrows in my particle diagram. The second type of energy, our potential energy, is specifically going to be phase energy in this case. And phase energy is simply the amount of space between particles. So basically, it's our density in our particle diagrams. And our evidence for this is what state of matter it's in. So solids are going to have less space between particles than liquids. So my evidence would be that it went from a solid to a liquid. As far as my energy bar charts go, let's start off and let's represent, I don't know, an ice cube. So ice cube is my system. And so with an ice cube, my kinetic energy is going to be cold. And so what does that mean? Well, maybe to me, cold is 1 bar of energy. However, maybe to you, cold is 2 bars of energy. Neither of those is wrong. You can do whatever you want. It's really up to you. The only thing is you want to make sure that whatever you make the energy, you don't, you pay attention to if you're going to have to increase or decrease the temperature at all. So that's not going to be in this case because we're not going to talk about that. That'll be in our next problem. So here I have a cold, and now for the phase. Phases are going to be determined, so the kinetic energy is kind of up to you. If 1 bar is cold to you, great. If 2 bars is cold to you, super. However, for phases are going to be set. A solid is always going to be 1 bar of energy. A liquid, its particles are spaced out a bit more than solid, to the point that they're able to move past one another. That's why liquids flow. And so a liquid has 2 bars of energy. However, a gas has a lot of space between particles, to the point that we can compress it. We did so in our syringe last week. And so a gas is going to be represented by 4 bars of energy. So there is no 3 bars for phase energy. Since this is a solid, that tells me that in my indication says a solid is 1 bar. So that means I have 1 bar of phase energy. So my total energy, I have a total of 3 bars of energy being represented. What would this look like in a particle diagram? Well, in a particle diagram, it's going to be a solid. So that means that I'm going to have particles that are close together. And it means my arrows are going to be short. Don't confuse phase with temperature, meaning the arrows are based on how hot or cold something is. It is not that it's a solid or a gas. So for example, here, my solid is going to have small little arrows because it's not moving very much. It has a low kinetic energy. Well, what if I want to represent a hot gas, or a hot solid? Sorry. Let's say I have a piece of metal that's glowing red hot. And so in this case, my kinetic energy now is going to be much greater because it's glowing red hot. So let's say that I have 1, 2, 3, 4, 5 bars of energy. Well, the phase, it's a metal, so phase is still a solid. Remember, it doesn't matter how hot or cold it is, it matters what state it's in. So now, in this case, my total amount of energy is going to be 6 bars. The 5 for the kinetic energy and the 1 for the phase energy. And so the way that this is going to look in my diagram is that my particles are still going to be the same spacing. The density didn't change. It's still a solid. I just want to make these a little bit more to scale compared to my ones beside it. So my particle spacing isn't going to change. They're going to be equally as dense. But what is going to change is my length of my arrows. And so yes, that means that your solids might get a little messy when drawing them. That's okay. Oops, that's a little too long of an arrow. Let's sit there and say here, and let's sit there and say there. So your arrows are going to get longer. How would this look different if my solid was going to a liquid? So let's say maybe I have ice that's going to go to water, to liquid water. I say liquid water because it's water even when it's ice. It's still H2O. The particles didn't change. All that's changing is the space between them and how fast they're moving. So when I go from ice, again, I have my tighter packed solid versus when it's a liquid, it's going to space out more. Like I just said, my ice is going to be a cold solid. So I'm going to have 1 bar each. So my total amount of energy here is going to be 2 bars. My ending part, my liquid water, well, I'm going to say that it warmed up a little bit because I know that to go through a phase change, after that, my temperature will increase. So I'm going to say that this isn't the same temperature as what my solid was at. It could be, but I'm going to say that it's not. I'm going to say that this is liquid water. So ice is at -4 degrees Celsius, just for reference. And let's say liquid water is at 25 degrees Celsius is what I'm representing. And so here, my kinetic energy is going to increase because I went from 4 degrees to 25 degrees. Don't even know what happened there. And so I'm going to say that I now have 4 bars of kinetic energy. My phase energy, remember, that's set in stone. That is predetermined. My liquid is 2 bars of energy. And so this gives me a total of 6 bars of energy. When I draw my arrows, the phase energy, when I draw my arrows, the kinetic energy is low, so I'm going to have very small arrows. However, in my liquid, it's a bit higher because I've heated up a little bit, so my arrows are going to be a bit longer. The length of them doesn't matter as long as I can clearly tell that your arrows have gotten longer. So the last thing we need to do is, I went from 2 bars of energy to 6 bars of energy. Where did this energy come from? And the answer is that the energy entered the system. I had energy added to my system. I had 4 bars of energy added to my system. And so since energy entered the system, enter is endothermic. Well, just to save some time here, let's do some manipulation. Now what I'm going to do is I'm just going to switch some stuff around here. And we're going to say that we went from liquid to solid. So here's my, trying to get these to line up properly. There we go. And so now I have a warm liquid water at 25. At 25 degrees Celsius. And over here, I have solid ice at -4. And so in this case, now when I look at my total energy, now I am starting with 6 bars. And I'm ending with 2 bars. So that means that energy left my system. Exiting the system means it's exothermic. The last thing that I forgot to do is up above I said system. Well, my system can be more specific. So here my system is going to be ice.